Hi, everybody. Here in this topic, we will be covering the concepts related to imbalanced class problem, cross validation, and overfitting. So, first, we will look into the concept of binary classification. So, binary classification would generally fall into the domain of mostly the supervised learning. Since the training data set is labeled, we consider the data set, training data set, to be labeled data set. And as the name itself suggests, it is simply a special case in which there are only two classes. So, some of the typical examples include the credit card fraud transaction detection, medical diagnosis, spam detections, etc. And also, there are various paradigms that are used for learning the binary classifiers, which include the decision tree, neural networks, Bayesian classification, and support vector machines. Then, like the binary classifier, we also do have the multi-class classification. So, in machine learning, the multi-class or the multinomial classification is the problem of classifying instances into one of three or more classes, classifying instances into, we also call it classifying the instances into one or two classes. So, it is called binary classification, and more than two classes will be our multi-class classification. And here input can be considered as belonging to the k number of classes, where k is always considered greater than 2. So here the input is associated with the class label, and it is a number from up to 1 up to k. And for the classification for a given input, we identify the class label, and also the input belongs to exactly basically one class. So while classifying the labels, we mainly classify different sort of things. It may be images, sound, desserts, or some other type of data set. So how does the classification algorithm actually understand? How to make the classification algorithms to understand this type of data? So for that, the data is supposed to be a categorical data. If we take an example of a pet variable, where a pet can be anything: a dog, a cat, or any other animal. For would likely be a pet. And for color variable, it can be different types of color names, for example, red, green, blue, yellow, something like that. So it should be any sort of the categorical data. So while processing the categorical data, how to actually convert the categorical data into the numerical data? So this involves actually two steps: the integer encoding and one hot encoding. So actually in integer encoding, if we'll look into the examples, so integer encoding, as a first step, each unique category value is assigned an integer value. So for example, red is 1, green is 2, blue is 3. And this is called a label encoding or an integer encoding, and is easily reversible. And one hot encoding, so for categorical variables where no such ordinal relationship exists, where some sort of order is not maintained, the integer encoding is not actually enough. So in fact, using this type of encoding, that is one hot encoding, and allowing the model to assume a natural ordering between categories, may result in poor performance and or unexpected results. And here the predictions can be halfway between the categories. So mm, we may have different types of applications, such as if we would like to recognize an image or classify an image. Suppose, let's say we have the handwritten character data set in this way. So depending on how the writing is actually being done, so based on that we do the classification. Or we also can consider an image of an object, where so which set of category of object actually the image belong to. So these are some of the applications the of the classification. So here the class imbalance problem. So it is the problem in the machine learning where the total number of class of data, so it may be positive. So if we consider the total number of class of data is positive and which is far less than the total number of another class of data which are negative. So this problem is extremely common in practice and can be observed in various disciplines, including fraud detection, anomaly detection, or medical diagnosis, or facial recognition. So any such type of applications. Then there are certain challenges uh, of the class imbalance problem. So here the evaluation measures such as the accuracy, they are not properly well suited for the imbalanced class. And while detecting a rare class in a big data set, it can be a case of finding a needle in a haystack. So these are some of the well-known challenges. So for evaluating the classifier, there are various metrics. So accuracy in classification problem is one of the number of correct predictions made by the model over all kind of predictions being made, and accuracy is a good measure when the target variable classes in the data are nearly balanced. So for accuracy, actually what happens, either the class can be C or negative of C or negative of C. So either you can have true, positive, false, negative, false, positive, true, negative. So this kind of probability will be there. So for calculating the accuracy, we can first consider it should be a summation of true positive and true negative divided by all the possible combinations together. So here, if we have the combination of true positive and false positive, so it will be termed as a symbol such as p dash, and for false negative and true negative, it will be n dash. So these are how the mm, different terms, and these terms are associated with calculating the accuracy for the error rate, sensitivity, and other measures such as specificity. So here for the error rate, actually error rate is 1 minus our accuracy, or also you can write it as false positive plus false negative divided by the whole combinations. Then so if we take into consideration the sensitivity and the specificity, so sensitivity actually measures the proportion of positives that are correctly identified. That is the proportion of those who have some condition affected and who are correctly identified as having the condition. And specificity is the measure of proportion of negatives that are correctly identified. That is the proportion of those who do not have the condition as unaffected, who are correctly identified as not having the condition. So these are some of the terms which are used for evaluating the classifiers. And some other type of metrics are also there. So one of them is precision, recall. Then next we have F measure. They are very effective for evaluating the accuracy of a specific classifier. So precision is the measure that tells us what proportion of patients, let's say we take an example, what proportion of patients that we diagnosed as having cancer has actually had a cancer. So predicted positives, people predicted as cancerous, are considered as TP, that is true positive, and false positive, and the people actually having a cancer are true positive. So recall is a measure that tells us what proportion of patients that actually had cancer was diagnosed by an algorithm as having cancer. So actual positive, and the people, actual positive means the people having cancer are true positive and false negative, and the people diagnosed by the model having a cancer are true positive. So note that the false negative is included because the person actually had a cancer even though the model predicted otherwise. And then There is another measure, which is the F measure, or it is also called F score or F1 score. And here it is considered as 2 multiplied by precision multiplied by recall divided by the summation of precision and recall. Then there is another measure of um, checking the accuracy of a classifier. So we can consider the example of confusion matrix. So how do we tell the machine learning algorithm that which one is the better solution? So to tell a machine learning algorithm or the researcher that model 2 is better than model 1, so we need to show that the model 2 is above is better than the model 1 above. So for that we need to have better metrics that just counting the number of mistakes made. So here we introduce the concept of true positive, true negative, false negative, and false positive. So true positive is actually an example that is positive and is classified correctly as positive, and true negative, which the example which is negative, sorry, true negative is actually is a negative and is classified correctly as negative. And false positive is an example that is negative but is classified wrongly as positive. And false negative is an example that is positive but is classified wrongly as negative. Then if we consider the accuracy, so based on the TP, FN, FP and TN, it can be calculated by the given formula. True positive plus true negative divided by summation of all of those four. True positive, true negative, false positive, false negative. This is a most widely used classifier metric as well. Then we will see accessing performance. So for accessing the performance of a given data is again interesting, and training and testing data are most important measures in this scenario. So training data performance is typically optimistic, considered as optimistic, and the reasons for this is the classifier in which we are going to do the classification, it may not have enough data to fully learn the concept. And for any sort of noisy data, the classifier may overfit the training data. Then next, if we look into the next concept, which is very much important, is the overfitting and underfitting. So overfitting. Okay, so before giving the definition of these two concepts, so let's see an example. So let us consider that we are designing a machine learning model, and the model is said to be a good machine learning model. So how we can say that? If it generalizes a new input data from the problem domain in a proper way. And this also helps us to make the predictions in the future data and that the data model has never seen. So now suppose we want to check how well our machine learning model learns and generalizes to a new data. So for that we have overfitting and underfitting concepts which are majorly responsible for the poor performance of the machine learning algorithms. So in an underfitting situation, a statistical model is said to have underfitting when it cannot capture the underlying trend of the data. And underfitting also destroys the accuracy of the machine learning model. While the overfitting, we call a model as overfitted when we train it with a lot of data, and it also trained with so much data that it starts learning from the noise and inaccurate data entries in our given data set. So appropriate fitting is a scenario when we have appropriate amount of data which are trained, which are used for training purpose, and also while testing the data, it is being tested correctly. Now, if we look into how the overfitting actually affects the prediction, the prediction error can be reduced by increasing the model complexity. So when you decrease the error on the training data, the model complexity also increases in the sequential manner. And then how overfitting can affect the prediction. So an error can be reduced by increasing the model complexity, while the test data can even affect the error and the model complexity in the similar way. Then, if we say how the overfitting can affect the prediction, so we can say that to reduce the underfitting and the overfitting, an ideal range of the model complexity is needed. Okay, so if we are decreasing the error on training data, then the model complexity is increasing, and somewhat we have a different trend here on error on the test data. So we should have an ideal range to have a more proper model complexity. Then moving over to training and validating the data. So suppose we have a full data set. So here we consider some part as a training data for training each model using that particular section of the data. While validating the data, we test each model's accuracy on the validation data. Somewhat validation data also helps in training the data properly so that it could be checked in a better way while testing it. Then next comes the k-fold cross validation method. So the cross validation is a resampling procedure which is used to evaluate the machine learning models on a limited data sample. And the procedure has a single parameter called k that refers to the number of groups that a given data sample is to be split into. So as such, the procedure is often called the k-fold cross validation. So when a specific value of k is chosen, it may be used in place of k in the reference of the model, and such that the k equals to 10, it can become as a tenfold cross validation. And cross validation is primarily used in applied machine learning to estimate the skill of machine learning model on unseen data. So this is also that is to use a limited sample in order to estimate how the model is expected to perform in general when used to make predictions on data that are not used during the training of the model. So if we see how the data is being validated, so first partition here is considered as the first partition in the k-fold cross validation. So we have a full training data set. Then while validating the data in the we this is the first partition, and we are performing the validation procedure on the data set, and this is considered as the first phase or first partition of the k-fold cross validation. Then here you can see that how there is a second partition and how they are validated. So after one partition, the second portion of the training data is being validated. This is the second partition. Now in the same way, if we consider a k-fold, that is 5-fold cross validation, so the given training data set, in the first partition this portion will be validated, in the second partition this portion will be validated. In the same way, each partition or section in the 5 steps in the 5 folds will be cross validated. So this is a more high level view of how the training data is being cross validated in each of the splits. If we consider the whole data set in the form of folds, 5 folds. So split 1, 2, 3, 4, 5. So in every folds, the data will be properly validated. And then after finding the parameters, we do the final evaluation on the testing data. So for the 5-fold cross validation, through the 5 folds or splits, the data is properly cross validated. The model is trained, and then after validating properly, we get the results. Next, if we want to get more concepts or want to explore more on the cross validation, so we can say that it generates an approximate estimate of how the model actually behaves in terms of the unseen data. So while considering different partitions, while doing the cross validation, it is considered as more robust than just a single partition. Then k-fold cross validation is also considered approximately k times, which is computationally more expensive than just fitting a model to all of the data together. So these are some of the concepts associated with the cross validation. So basically, if we want to understand the k-fold cross validation, the generalized picture is we actually first train the data, validate data, and average over through each partition. Let's say we have k partitions and k equals to 10 here. So data will be trained, validated, and averaged over those 10 partitions altogether. So actually implementing this k-fold cross validation in the scikit-learn, in Python scikit-learn library implementation. So this is one code snippet showing how it is being implemented. So these are some of the libraries, and here you need to import the trend test split, and we are using the support vector machine, and you are actually loading the data set as the features and the target. Then you are dividing the data set into the trend and the test data, and using the trend test split function, you are splitting the data all together. Then next, you are fitting the model and setting the kernel as the linear kernel. And when you try to print the scores by fitting the data, you will get these are the accuracy scores performed through each of the cross validation or the cross validated scores. And here cross validation parameter is set as 5, means in 5 partitions the model will be trained properly.